We've now spent a fair amount of time naming ionic compounds and molecules, but now it's time to count them. The thing is, molecules are very, very small, so we're likely going to want to count a lot of them all at once. To help us, do you remember this worksheet from earlier in the year? Something we didn't pay much attention to last time was mass. Note here that there's a mass conversion where 1 AMU, or 1 atomic mass unit, is equal to 1.6606 times 10 to the minus 24 grams. And note that the different atoms have different masses expressed in atomic mass units. I'm not so concerned with those, but what is interesting to point out is that carbon is exactly 12 AMUs. That's interesting, isn't it? Turns out we actually define an atomic mass unit as 1/12 the mass of a carbon-12 atom. That works out to roughly 1.66 times 10 to the minus 24 grams. It's a really cumbersome number to remember, and it's a very, very small number. In fact, I'm not sure we're concerned with the mass of a single atom, as they're individually so small. But maybe we can use the mass of an AMU to help us find an easier way to count atoms, and then eventually to mass them in meaningful amounts. To do that, let's turn back to the worksheet. I'm curious about the mass of one hydrogen atom and one carbon-12 atom in grams. To do that, we can set up a quick conversion. Hydrogen is 1.0078 AMUs, which if we convert to grams, is going to be very small. Likewise, carbon, which is 12 AMUs, if converted to grams, is going to be very, very small. That is to say, we're not really concerned with the mass of one atom. What about a dozen atoms of carbon? Well, very small times 12 is still a very small number. What about a million, or 4.35 times 10 to the 6 million atoms of carbon? Notice here that our exponent is times 10 to the minus 24, so even if we're talking about a million atoms, we're still talking about a very small mass. Now it gets interesting. Let's say I was concerned about the mass of not one, not a dozen, not a million, but 6.022 times 10 to the 23rd atoms of carbon. Let's set up my conversion again. When I do that out, I find that comes out to exactly 12 grams. And that is interesting. Turns out we define that number as a mole. 6.022 times 10 to the 23rd things. That was all a really long-winded way of coming about that number, but I think what's important to remember about a mole is the number of things such that one atom in AMUs has the same numerical value as a mole of atoms in grams. Likewise, a molar mass, just the mass of a mole of objects. Let's keep these terms in mind for later. Another way to look at that. A single hydrogen atom has a mass of 1.0078, or about 1 AMU. Therefore, a mole of hydrogen has a mass of 1 gram, or hydrogen has a mass of 1 gram per mole. A single oxygen atom has a mass of 15.9960, which is about 16 AMU. So a mole of oxygen has a mass of about 16 grams, or oxygen has a molar mass of 16 grams per mole. So the values on the periodic table represent both the mass in AMUs of a single atom and the mass in grams of a mole of these atoms. That's important to remember. So the question is, how big is a mole of something? Pictured here is a mole of aluminum, a mole of carbon, a mole of iron. If you take about 2 or 3 deep breaths, you should have just inhaled about a mole of air, which is a combination of oxygen, nitrogen, and some other things. Or if you take a small sip of water, that's about a mole of water. Interestingly, molecules are so small that if you talk about larger objects, a mole of oranges would cover Earth, all the surface of Earth, to a layer about 5 miles deep. A mole of donuts, as delicious as that would be, would stretch all the way to Alpha Centauri. Here's some examples of moles. If we had a mole of carbon atoms, 6.022 times 10 to the 23rd carbon atoms, they would have a mass of 12 grams. Hydrogen, when it's a molecule, is 2 hydrogens stuck together. So if you had a mole of hydrogen, it would have a mass of 2 grams, because each hydrogen is about 1 gram, so 2 of them would be 2 grams per mole of hydrogen molecules. Methanol is composed of a carbon atom, 4 hydrogen atoms, and 1 oxygen atom. So the mass of a mole of methanol can be found by summing the mass of a mole of all those different atoms. And that works out to 32 grams. 4 moles of hydrogen, 1 mole of carbon, 1 mole of oxygen. These are all examples of molar masses. So let's do a calculation here to find the molar mass of water. Hydrogen, for our purposes, we can say is 1 gram per mole. Oxygen, we can say is 16 grams per mole. So if we add those things up, we get 1 plus 1 plus 16 equals 18 grams per mole. What that means is 1 mole of water has a mass of 18 grams. Or put another way, 6.022 times 10 to the 23rd molecules of water has a mole of 18 grams. While it's a big number and can be hard to remember at times, think of a mole just like a counting number, just like a pair or a dozen or a score or a gross. It just happens to be a very large number of objects. But again, it needs to be because molecules are so small. At the end of this lecture, you'll have the opportunity to do some practice problems calculating molar masses for the compounds shown below. In each case, add up the molar mass of each of the atoms. If there's 3 hydrogens, you need 3 moles of hydrogen. If there's 4 oxygens, you need 4 moles of oxygen. Add up the molar mass of all those atoms, sum them together, and that's the molar mass of the compound. This question reads, what's the mass of 2 moles of carbon dioxide? For starters, we should figure out the mass of a single mole of carbon dioxide. Carbon is 12 grams per mole. Oxygen is 16 grams per mole. However, there's 2 oxygens in this compound, so we need to add up 12, 16 times 2 to find that carbon dioxide is 44 grams per mole. Using that number, let's start with what we're given, 2 moles of carbon dioxide. Put it over 1, and multiply by this conversion factor. This molar mass can act as a conversion factor. 44 grams equals 1 mole. Our moles will cancel, and we'll find that 2 moles of carbon dioxide have a mass of 88 grams. At the end of this lecture, you'll have the opportunity to do some practice problems of converting the following into grams. In each case, you'll need to find the molar mass of the compound and set up a conversion where you start with the number of moles and then multiply by the molar mass to cancel out moles and replace it with grams. The last question reads, how many moles of water are in a 25-gram sample? It's going to be similar to what we just did, but we're going to use the molar mass as a conversion factor to go from grams to moles instead of from moles to grams. Just like before, let's figure out the molar mass of water. If we sum the mass of hydrogen, and oxygen, we get 18 grams per mole. Now I want to set up my problem, starting with what I'm given. Using a conversion factor of the molar mass, this time I'm just going to flip it upside down. Say that 1 mole over 18 grams is my conversion factor. I'm going to get the answer of 1.39 moles. That is to say, if I had 25 grams of water, there would be 1.39 moles of water molecules in that sample of water. The moles may be a more useful number for quantifying molecules, because if I were to express how many that actually is, I would need to multiply 1.39 by 6.022 times 10 to the 23rd, and it's going to be a huge cumbersome number of water molecules. So let's review the terms we have. A mole is 6.022 times 10 to the 23rd things. A molar mass is the mass of a mole of objects. It can be expressed in grams per mole or 1 mole per some number of grams. Both of those terms are convenient because they both equal 1. And because they equal 1, they can be used in conversion factors. So in converting grams to moles, we would want to start with our grams over 1, multiply it by 1 mole over grams, and get moles. Or in converting moles to grams, we would want to start with the number of moles we're given and multiply it by grams per mole to get grams. In both cases, these molar masses we're using depend on whatever substance we're given in the problem. This is going to be really important later on in the class when we begin looking at reactions and trying to figure out how much goes into a reaction and how much comes out. Our reactions are written in terms of moles, not in terms of grams, so trying to figure out those ratios, it will be essential that you can convert from grams to moles. At this point, go back, look at the lecture, and do the practice problems of finding molar masses, converting grams to moles, and converting moles to grams. I'd like you to work alone for the first several minutes, and then compare answers with the people sitting around you. But it's very, very important that you be able to calculate all 3 of these kinds of problems on your own. I was really hoping that I could be in class today, and I'm disappointed to not be able to be there. So instead, I'll leave you with a picture of a mole inside of a beaker. Enjoy, and have a good weekend.